have a 350 Newton sign hung from the end of a 1.5 meter long 200 Newton beam. The cable is attached to the end of the beam and connects to the wall. So let me draw you a picture here. So here's our beam. There's a cable out here attaching that beam to the wall. The cable makes an angle of 40 degrees from the horizontal. So this angle is 40 degrees. Our sign is out here at the end. I don't know what the sign says. I'd like to know what the tension is in the cable. Number 1. What do you expect the net torque to be on this beam? Hopefully 0, otherwise it's going to fail in its responsibilities of holding up the sign. We know net torque is I alpha, but we don't want the beam to rotate. We want it to stay stationary. We want it to continue holding up the sign. So that angular acceleration is 0, so the net torque must be 0. Now technically also the net force must be 0 as well. Both of them must be satisfied. When we talk about objects being in equilibrium, both of these conditions must be met. The net force must be 0 and the net torque must be 0. It is possible to have a net force that is 0 and a net torque that's not 0. It's like our pulley example. The pulley itself isn't going anywhere, it's just spinning. The net force on it is 0, but the net torque is not. It's also possible to have a net force that's not 0 and a net torque that is. Something that just slides, moves along a straight line. In equilibrium, you must meet both conditions. The net torque and the net force must be 0. So number 1, it's really good to draw a free body diagram. Our object with all of the forces acting on it. Well, we have our object. The beam is the thing that connects the sign and the cable and everything together. So let's draw the forces on the beam itself. The sign is exerting a force. 350 newtons is the force of gravity. That is the weight of the sign. So the sign is at the end, so that 350 newtons is applied at the end. The cable has a tension. That's what we're looking for. We want to know how big that force of tension happens to be. The beam itself weighs 200 newtons. Where would I draw the force of gravity for the beam itself?
0.75.
At the center of mass. So right at the center. I'm assuming it's a uniform beam. So, what was it, 200? Now we have 2 more forces. What forces have we missed? What's the wall doing? The beam's touching the wall, so the wall must be doing something to it.
Which is the moment occurring with the force.
Pushing inwards and upwards. I'll call them F1 and F2. Okay. If the wall disappeared, the beam would go that way and down. So the wall has to be pushing out and up in order to keep that beam in place. Now I'm going to go ahead and let's look at the net torque first. Now when we talk about torque, we need to be able to say the lever arm, how far away from the rotation axis, as well as the force. So that means we need to choose a rotation axis. Since this beam is not rotating at all, you can choose any place on the beam that you want to be your rotation axis. That's not a problem. I would suggest choosing a place that has maybe a couple forces acting at it. For example, I would suggest putting our rotation axis right here. Anyone venture a guess as to why? The net torque, the torques due to these 2 forces will be 0. Exactly right. F1 and F2 will not produce torques around that rotation axis because the lever arm is 0. Any force acting at the rotation axis will not produce a torque. That's fabulous. That means F1 and F2 are not going to show up in our net torque equation. Okay. The 200 newtons, the 350 newtons, and the force of tension will. All of those are producing torques. All of them have a lever arm and a force perpendicular. Alrighty, so the 200 newtons. The lever arms from the rotation axis out to the force. So how long is that? 0.75. Half the 1.5. So from the wall to that 200 Newton force is half the length of the beam. So that's the lever arm. The force is 200 newtons. If that were the only force, so if the beam was pinned to the wall and that was the only force being applied, which direction would it make the beam rotate? Clockwise. So we need to decide, do you want to call clockwise or counterclockwise positive? Doesn't matter. We just need to decide. You want to call counterclockwise positive, so clockwise would be negative. Okay, that's fine. We just need to make it negative then. Okay. The 350 newtons. If we draw in the lever arm for that, we need to go all the way out to the end. So how long is the lever arm? 1.5 meters. The force is 350 newtons. By the way, they're already perpendicular. That's not why I didn't ask and point that out last time. Both the 200 newtons and the 350 newtons are perpendicular to the rod. So we already have the perpendicular components. Will this one be positive or negative? Also negative. Force of tension. That one's going to make it rotate counterclockwise, so that'll be positive. How long's the lever arm for the force of tension? 1.5 meters. Force of tension is acting, it's pulling on the end of the rod, end of the beam. So it's 1.5 meters away. Now it's only the component of tension that's perpendicular to the beam. We want this piece, which is the same as this piece. Force of tension is the hypotenuse, but we need the vertical side. How do we get the vertical side? Right, sine of 40. So force of tension sine 40 gives us this perpendicular piece. So force of tension sine of 40 gives us the perpendicular piece. It's only the perpendicular component that's causing the torque. Force of tension has a component that's parallel, but it doesn't produce a torque. So these are all the torques, so this all has to add up to be 0. So force of tension is our only unknown. Force of tension, I'm going to take these guys to the other side. So 1.5 divided by 2 is 0.75. I get 700 newtons. If anyone disagrees, I know. That's the tension in the cable. Exactly right. So that is the actual force of tension at that angle.
So, if we wanted to know the force of tension that the beam is using to push
certainly, if we wanted to know the force that the wall's pushing back, which is the same as the wall's pushing on the beam, we would need to sum up the forces in just the x direction. So we'd have F1 to the right minus the horizontal component of tension, so force of tension cosine 40. That would have to equal 0 because it's not accelerating along the x direction. So F1, that horizontal force that the wall is exerting on the beam, is simply the force of tension, 700 newtons, times the cosine of 40 degrees. That will give us F1. F2, we would need to add up all the forces in the y direction. We'd have F2 plus the force of tension sine 40 minus the 200 minus the 350 would all have to equal 0. So you just add up the forces in your y direction. Just using a traditional Cartesian coordinate system. So we'd have F2 plus Ft sine 40, because that's the vertical component, minus 200 newtons, minus 350 newtons. That would all have to equal 0, because it's not accelerating vertically either. That would allow you to find F2, the force that the wall's pushing upwards on the beam.
Question.
Yes?
If you found F2, couldn't you just go ahead and use the F2 to find Ft?
But we can't find F2 without knowing Ft. But yeah, if you happen to know what Ft was, then certainly. But the whole reason we can solve for F1 and F2 now is because we know Ft. Okay. So equilibrium problems, problems in which the object is not going to move, net torque and net force need to be 0. Oftentimes in the equilibrium problems, the net torque equation will give you either what you want or at least one piece that you can then work backwards and solve for. So I generally, if I see an equilibrium problem, I usually start with the net torque equation and then work from there if I need more information.